Now we've come to relative velocity. You'll come across this topic a lot when you get to kinematics and dynamics. So the class right after statics and dynamics. You'll do so much relative velocity and relative acceleration. So we are to find the velocity of A with respect to B, which is not the coordinate systems that we're usually looking at. And then we're to find theta dot and r dot. We've done a lot of this in this chapter, looking for the coordinates of velocity and acceleration in a different coordinate system. But this first part is a little bit new. Before we move on to solving the problem, let's talk a little bit about the relative velocity. If you're to look at the velocity of A, and we're going to slide down the vector using transmissibility to where the arrowhead is pointing at A. And this is the velocity of A, and it's actually with respect to the ground, this point here, because the velocity of the ground is 0. Makes sense. If you subtract 0, it's the exact same. So oftentimes, that with respect to the ground is left off. And we have this coordinate system connected to velocity of A, which is AY hat and AX hat. If we're to do the same thing with B, where we slide the arrowhead down, velocity B with respect to G, and you also have BY hat and BX hat. But what's this ground that we've been talking about? Well, it kind of makes sense that it's going to be GX hat and GY of hat. And the velocity of the ground is equal to 0. So the tip and the tail of the velocity of the ground are here, and we're going to call this the ground. Well, why is this important? Because this ground coordinate system, the one that we always use but never think about, is how you're going to connect these two vectors together. Let's pull this vector and this vector and stick them together because they are both related to the velocity of the ground. Velocity of B with respect to G, and that makes this point B and this point G. And we also have the velocity of A with respect to G, and that makes this point A, and once again, this point is G. So now let's take a step back from the velocity and thinking about what's going on and just think about vectors, because mathematically we can define velocity in vectors, and that helps us identify what they're doing with each other. We don't have to think about, okay, so if it's moving this way, you do this. Yeah, you can think about that, and conceptually that's what's going on, but now let's think about it in a pure mathematical sense. So this arrow, if I was to draw it, would be A with respect to B. And since we're dealing in velocity, we're going to put velocity there. I could also do it the exact opposite way and draw B with respect to A. So either way, we can identify these in terms of each other by taking out this ground point. If we were to just draw one side of the story, G to B to A, we could say that we would add B with respect to G to A with respect to B, because you travel adding A with respect, or B with respect to G, then you add A with respect to B. You could also do the same movement from G to A by just doing that one small vector that we have. So this is G and this is A. And that vector is A with respect to G. And both of these get us from point G to point A. Even though there's an extra step here, it still does the same thing, so that means they're equal. This equation should be very familiar to you, although often it is written without the ground, because it's a given that it's with reference to something that's 0. And you get this equation. And that is where this equation comes from, and it's really helpful to remember which one's which and how you're supposed to use A with respect to B, because you could also write it the velocity of b equals the velocity of a plus b with respect to a. And that would be traveling this from G, A to B, just adding from G to B. However you want to do it, if you're solving for A or B, but be sure that these are related to each other correctly. Okay, what is another way that we could solve for vectors that are in a triangle similar to this? And we did this a lot at the beginning of the semester, solving for vectors. So you should think about what we've looked at before, the law of cosines and the law of sines. It should come to no surprise to you, seeing how you've worked a lot of problems with the law of cosines and the law of sines. And in this problem, it's actually easier for us to look at it as the law of sines and cosines because we're given this angle here, which is 45 degrees, and we're given the magnitude of the velocity of A with respect to the ground, and we're given the magnitude of the velocity of B with respect to the ground. So we can then define this as 135, and you conveniently have two sides of the triangle, and you have an angle.